Dear students, in this sixth lecture of semiconductors, we are going to calculate the equilibrium electron concentration and carrier concentration for p-type semiconductors. Equilibrium concentration of electrons. Since the position of the Fermi level is already we calculated in the previous lecture, EF is equal to ED plus EC by 2 plus KT by 2 log of ND by NC. For the extrinsic semiconductors, the concentration of the electrons in the conduction band is N is equal to NC exponent of minus EC minus EF by KT. Equation number 2. The free electron concentration in the conduction band is obtained by substituting the value of EF from equation 1 into equation 2. N is equal to NC exponent of ED minus EC by 2 KT plus 1 by 2 log of ND by NC. Is equal to, by simplification we get the ND NC of under root exponent of ED minus CC by 2 KT. N is equal to ND NC under root exponent of minus del E by 2 KT. Equation number 4. Here del E is equal to EC minus ED, represents the ionization energy of the donors. The donor level energy ED and the conduction band edge energy EC. The difference of those is equal to del E, which is required for the ionization of the donors. This shows that the carrier concentration at the moderate temperatures varies as ND and root. The electrical conductivity of an N-type semiconductor can be calculated from sigma is equal to En mu N. Here is the charge, N is the number of the electron concentration, and mu N is the mobility of the electrons. Is approximately equal to E and D plus mu N. ND plus is actually the ionized donor atoms, where it has been assumed that the conduction is mainly due to electrons. Knowing the electron concentration N and the electron mobility mu N at any given temperature, the electrical conductivity can be calculated by using equation 5. The temperature dependency of electrical conductivity for an N-type germanium is given in fig here. The conductivity versus temperature for a typical N-type germanium sample here. We have seen that with the increase of the temperature, the conductivity is going to firstly decrease, then again making some parabolic shape. The following conclusions can be drawn from this curve. 1. Starting from the very low temperature about 10 Kelvin corresponding to the point A, the conductivity increases with the rise in temperature. This is due to increase in the number of conduction electrons as a result of ionization of the donors. The conductivity attains a maximum value point B when all the donors are ionized. The temperature corresponding to this is about 50 K for a moderately doped N-type germanium. The conductivity decreases with further increase in temperature up to about room temperature point C and is attributed to the decrease in the value of mobility with the rise in temperature. There is also an increase in the intrinsic conductivity, but to a lesser extent. The sharp rise in conductivity from C to D is due to the large increase in intrinsic conductivity, which offsets the decrease in mobility. These are the conclusions from the graph. Carrier concentration for p-type semiconductor. The case of a p-type semiconductor can be treated in the same way as that of n-type semiconductor. The energy level diagram for a p-type semiconductor is shown in fig 1. The acceptor impurity atoms occupy the acceptor levels EA. Here band model diagram for the p-type semiconductor fig 1 representing the valence band and the conduction band, and the horizontal line EV above the on the valence band is the valence band energy, and the EA is the acceptor level, and between acceptor level and the valence band EV there is a EF, that is the Fermi level of the p-type semiconductors. The acceptor impurity atoms occupy the acceptor level EA, which lie above the valence band. for T greater than 0 Kelvin. A part of these acceptors is ionized by acquiring electrons from the valence band, thus creating holes in the valence band which cause p-type conduction. Apart from these holes, some thermally generated holes are also present in the valence band. If Np and Na and Na negative represents electron concentration in the conduction band, hole concentration in the valence band, total acceptor concentration, and the concentration of the ionized acceptors respectively, then P is equal to N plus Na negative. Because the acceptors are taking the electron from the valence band, therefore these are the negative ions, neglecting N in the comparison with Na negative for p-type semiconductors, because there are number of electrons equal to the number of protons if there are Na are the smaller than the N. P is equal to approximately Na negative, because here the number of holes are also generating from the electron hole pair, and the holes are also generated by the p-type semiconductor. Therefore the holes are much higher as compared to the number of the electrons. Therefore we ignore the number of electrons. We get the concentration of ionized acceptors is given by Na negative is equal to Na into F of Ea is equal to Na over 1 plus exponent of Ea minus Ef by Kt, assuming Ea minus Ef to be large as compared to Kt. Actually Kt is very less quantity, therefore the equation 2 can be written as Na negative is approximately equal to Na exponent of Ef minus Ea by Kt. Means we ignore the 1 and we take 1 plus exponent of Ea minus Ef by Kt is equal to exponent of Ea minus Ef by Kt, and when it shifts upward, then the negative sign changes the exponents values. The whole concentration in the valence band is given by P is equal to Nv exponent of minus Ef minus Ev by Kt. Here Nv is the concentration of the holes at the valence band H, representing Ef the Fermi level, and Ev is the conduction valence band energy, and divided by Kt. This is the equation number 4. Using equation 3 in equation and equation 4 in equation 1, we get Nv exponent of minus Ef minus Ev by Kt and is equal to Na exponent of minus Ef minus Ea by Kt. This is equation number 5, which on simplification gives Ef is equal to Ea plus Ev by 2 minus Kt by 2 log of Na by Nv. As described earlier, the Fermi level at the moderate temperatures lies near the middle of the acceptor level and the top of the valence band. It moves upward with the increase in the temperature and finally coincides with the intrinsic level as shown in the fig 2. The expression 6 is not valid at very high temperature where N cannot be neglected. The fig 2, variation of the Fermi level with temperature and impurity concentration for silicon. For different impurity concentrations, we have seen that the valence band Ef minus Ei, the valence the acceptor level for the p-type semiconductors, the Fermi level is going to upward with the increase of the temperature, and it meets with the zero line that representing the Ef minus Ei is equal to 0, means the Fermi level of the p-type materials at high temperatures coincide with the intrinsic level. Since Ni is equal to Nc exponent of minus Ef minus Ei by Kt and Pi is equal to Nv exponent of minus Ei minus Ev by Kt. Using equation 4 and 7, we obtain the expression obtained to N-type semiconductors. For p-type semiconductors, P is equal to Ni exponent of minus Ei minus Ef by Kt. It indicates that the equilibrium hole concentration approaches the intrinsic carrier concentration as Ef approaches Ei. Also, P increases exponentially as Ef moves away from Ei towards the valence band. An expression for the hole concentration in the valence band can be obtained by using equation 7 into equation 4 as in the N-type semiconductor case. The electrical conductivity of a p-type semiconductor is given also P approximately equal to Na negative, and the sigma P is equal to Ep mu p is equal to E N a negative mu p. Here sigma p is the conductivity of the p type semiconductor conductors is equal to E p. P is the concentration of the holes, and mu p is the mobility of the holes, and while the E Na negative is the ionized acceptors, and here the concentration of the minority carriers is ignored. Uh, the variation of the conductivity with temperature is similar to that for the n-type semiconductor. It also follows from equation 9 that the increase in the concentration of the either type of the impurity atoms increases the conductivity of a semiconductor. For impurity concentration ranging from 10 to the power 22 to 10 to the power 22, 10 to the power 22, 10 to the power 22 per m cube, the resistivity of silicon and germanium varies from 10 to the power minus 3 to 10 to the minus 1 ohm meter. If doping is heavy, 10 to the power 23 to 24 atoms per m cube, the conductivity of semiconductors becomes comparable to the metals. Such semiconductors are called degenerate semiconductors and find applications in high power and high frequency devices. Mixed semiconductors. In a semiconductor containing N and P type impurities, the law of electrical neutrality is written as Nd raised power plus P plus Na negative plus N. Means donors ionized plus the whole concentration is equal to acceptors ionized acceptors plus electrons. Taking Nd plus is equal to Na negative and Np is equal to Ni square, we obtain P is equal to N is equal to Ni. This shows that for equal concentration of donors and acceptors, the semiconductor behaves as the pure or intrinsic semiconductor. All the ionized acceptors combine with free electrons of the donors, and all the ionized donors combine with free holes of the acceptors to produce no net free carriers. For Nd plus does not equal to Na negative, or simply Nd does not equal to Na, donors and acceptors are assumed to be ionized. The semiconductor behaves as n-type or p-type depending on the relative magnitudes of the Nd or Na, and the cases described above become applicable.